If you recall your studies from pre-calculus and maybe before, you may have talked about an idea about increasing functions. So what an increasing function means is that if I have an interval, as the values go from left to right in that interval, so as the values increase in that interval, the function values also increase. Each function output gets larger. That is an increasing function. Now, if I take the same interval and as I go from left to right, so as the values get larger for the inputs, if the function outputs get progressively smaller, that function is known as decreasing. So here we have an example function, the graph of an example function. What we see is as the x values, or the input values, go from left to right, the function value outputs go down. So this function is decreasing on this interval. Now here we see a turnaround, and the function increases on this interval, so it keeps coming up. Notice that here the function is constant, so it's neither increasing nor decreasing, it's simply staying the same. And then in this interval, the function values are increasing, and finally in this interval, they're decreasing. Now there's an interesting tidbit here as well, is that it's decreasing and it kind of curves this way, it kind of curves inward here, but it curves outward there. And even though it has two types of curvatures, the function is still decreasing on that interval. So what we would like to do is we would like to use the techniques of calculus to see if we can't characterize these functions in a specific way using the techniques from calculus. And it turns out we can. There's a technique called the first derivative test. So if we have a function that's continuous on some closed interval, and differentiable on the open interval. So I can take some closed interval and then I can take make sure that it's differentiable on an open interval. If the value of the derivative is positive in that open interval, the function is increasing on the closed interval. Now, if the function value is negative, if the value of the derivative is negative in that open interval, it's decreasing on the closed interval. And if the value of the derivative is 0, it's constant. Now, this is like the definitional way to look at it, but in practice, you go the exact opposite. What you do is you take the derivative of a function, you figure out where it's defined, and then you say, okay, where's that derivative positive? Where's that derivative negative? Where is that derivative equal to 0? And that's all you really have to do. So if we were to look over here and we were to take this function's derivative, let's suppose for a moment that it's completely differentiable. Now it won't be differentiable here at 0 because that limit's going to go off to infinity. But if we take a look at this thing's derivative, if I were to take the slope of the tangent line, notice that the slope of the tangent line is negative here. And that's, if I were to take, just a tangent line each of these places, it would be negative. That tells me that the derivative is negative here. And notice that there's a turnaround point. Remember, we talked about the idea of critical values, critical numbers, and we found the locations where the derivative was equal to 0. So we found that critical number, and then we had the behavior where it changed, the value of the derivative changed. So we knew that we had a local minimum, and now we have an increasing interval. And over here we actually have it changed to be the slope of the tangent line is 0, but it stays 0. So since it stays 0 in that range, it's constant, then it has one last value at 0 and starts to increase again, changes to 0, and starts to decrease. So that's the idea, is the slope of the tangent line goes down, stops, comes up. So think about it kind of the way the motion would behave on like a roller coaster as you go down, kind of how you feel the changes move. That's more of an acceleration. This would be more like velocity, but the idea is the same, that it's giving you a feel for how the motion of the function is going. And you'll notice that I pieced together the idea of when we were talking about increasing and decreasing functions and how we were able to characterize values as local minimums or local maximums. And what you'll see is we're not only going to combine some of this, we're going to combine further techniques to really characterize functions. What you find is there's a lot of power in calculus because you can take a defined function, you can apply a sequence of tests to it, and you can understand a whole lot about a function without ever having to plot points.